Good morning, Year 11. Today we're going to look at calculating the rate of reaction. The rate of reaction is just a measure of how quickly a reaction takes place. We can measure it in several ways. We can look at the quantity of reactant that's used every second, or we can look at the quantity of product that's formed every second. And we can also look at it in terms of mass. As you can see here, we're using a top pan balance to measure how mass changes in a reaction, or we can use volume. If we've got a reaction like the one here, which is producing a gas, hydrogen in this instance, we can measure the volume of gas that's produced every second. If we're measuring mass, it will give us the rate of reaction in grams per second. If we're measuring volume, we're going to get the rate of reaction in centimetres cubed per second. We'll usually be given a graph that looks something like this. This one's got a volume on the y-axis, so this is clearly using a setup like this to measure how much gas is produced over a certain amount of time. You might have to plot your own. It only takes a couple minutes to plot a graph, and it doesn't make it any more complicated. It's the interpretation and the analysis of the graph that's really important. So if we take a look at our graph to start with, we might have to explain the trend or the pattern that our graph is showing. So if we have a look at the start of the graph, we've got a really steep slope, or a really steep gradient. This means we've got a large change in volume for a short time. This means that there is a high rate of reaction. As the reaction progresses, if we have a little look a little bit further along, when we get to this area of the graph, the gradient isn't as steep as it was down here. So we're producing less gas for every amount of time we're looking at. So we have a shallower slope, or a shallower gradient. Hence we have a lower rate of reaction. And then finally, if we look beyond, say, 90 seconds, beyond this point here, the line is horizontal. So if we've got a horizontal line, that means the rate of reaction is 0. So we're not producing any more gas over whatever the time period here is. So this means that either all the magnesium has reacted or all the acid has reacted, because there's no more reaction taking place. The reaction stopped. There are two things, or two calculations, that you might need to do on this one. The easiest one is to work out the mean rate of reaction over a particular time period. So we've chosen to look at 20 seconds here, but they could give you any period of time. So the most likely one will be somewhere towards the left hand side of the graph. So let's have a look at the first 20 seconds. So this is where the reaction started at 0 seconds, and we're only interested at that part there. We're going to use the equation rate of reaction equals, well, it's volume in this instance, volume of gas produced over the time taken. And as we can see, after the first 20 seconds, if we read across here, we're halfway between 20 and 40, so that suggests to me that it's 30 centimetres cubed, and the time it took, well, that's just 20 seconds. That gives me, if we were to type that into a calculator, 1.5 centimetres cubed per second. So that method is quite straightforward. I think we'll all be quite confident doing that. They might ask us to do something that's a little bit more complicated. If they're asking us for a rate at a specific time, then we need to do a little bit more work. This question asks us for the rate at 40 seconds. So if we go back to our graph, here is 40 seconds. Now, if we were to try and work out the average rate, just like we did in the previous question, that isn't going to give us the answer we're looking for. So we have to do two things. If it's a specific time, we have to draw a line called a tangent. So we'll need a ruler to do this. I'm going to place the ruler so it's touching the curve at the time that's been specified. So at that time is equal to 40 seconds. Now I need to make it as symmetrical as possible. So if I were to have it like this, then it's too far down on this side, so that's not symmetrical. If I were to do it like that, too far down on the left, so it's not symmetrical. And it's a judgment call, really. You have to be quite careful. I think that looks sensible to me, so I'm going to hold my ruler down and I'm going to draw it across like that. So this tangent is a line that touches the graph at the point we're interested in, and this line will have a gradient which is equal to the rate of reaction at that time. To calculate the rates, I'm going to draw a triangle using that line because I need to work out the gradient of that tangent. So if we just annotate what we're doing down here, so our rate of reaction is the gradient of the tangent, which is equal to the change in the y-axis over change in the x-axis. So let's go back to our graph and see if we can work out what those values are. If we have a look at the bottom here, this appears to be 20 centimeters cubed if we read it across, and at the top of our triangle here, that looks to me like it's 60, 70, 72 centimeters cubed. So the difference in these two numbers, so it will be the final minus the initial, that gives us 52 centimeters cubed. So that's the difference in gas. That's how much gas has been given out over this time period. Well, over here on the x-axis, it starts at 0 and it finishes at 80. So this side is just 80 seconds. We go back to our equation below, so the change in y was 52 divided by 80. Type that into a calculator and that will give us 0.65 centimeters cubed per second. And we can have a bit of a common sense check here. This rate is much lower than the rate we calculated earlier. So when we look at our graph, we should notice that the gradient of our tangent is much less than the gradient to the slope for the 20 seconds. So this, yeah, that's quite a steep gradient, whereas this is much shallower. So yeah, that agrees with what we've just calculated.